recording. All right. Lecture 9, everybody. Let's get started. We have 2 lectures left on plane truss analysis. I want to talk a little bit about homework schedule and really the class schedule for the next couple weeks. So first off, today and Wednesday will be our remaining 2 lectures on plane truss analysis. We're going to look at method of sections on Wednesday. Today, I've got a couple other things I want to look at on method of joints, and that is solving a joint with 2 diagonal members and utilizing some matrix algebra to be able to do that. And there are other ways of handling trusses like this, but I kind of want to expose you a little bit to the idea of using matrices because we are going to be looking at matrices a little bit later this semester, so I kind of want you to be aware of that. I also want to talk about identifying zero force members today in a truss. As you saw in our last example, we had a truss member that carried no load, and that is not the first or the last time we will deal with that. Or that was the first time, I guess. That was the first time, but it won't be the last. We will have zero force members in a number of different scenarios. I want you to have a quick way of identifying those. Friday is going to be movie time a little bit. In other words, I'm not going to give you a homework and we're not going to do an in-class example. Friday, we're going to begin our discussion of truss deflections. Okay? So Friday is sort of a review of the theory, and then Monday we'll implement it. So what I'm going to do is I'm going to give you a homework on Friday, but it's not going to be due until the following Wednesday. Okay? Does that make sense? Truss deflections are not any more difficult, but the way to solve, if you want to do a truss deflection problem, you sort of have to solve a truss twice. So I want to give you a little bit more time on it. Next Wednesday, we're going to introduce our project, okay, our class project. Okay, let me actually pull up that schedule. So let me zoom in here. So the way this is going to work is so we're going to do 2 more lectures on truss analysis, 2 lectures on truss deflection. On Wednesday, I'm going to introduce your analysis project. It has 2 submittals. The first submittal is right around the October break, and then the second submittal is right around Thanksgiving. Friday, we review for our first exam, and then Monday, September 23rd, we celebrate. Because I know you're probably getting into the point where a lot of your classes are thinking about quizzes and celebrations of learning. And so that's when our celebration is, Monday, September 23rd. Sound good? Okay. The only other thing I wanted to mention before we move on, well, 2 things I wanted to mention. First, I was noticing something in class that it seemed that I think it has to do maybe with the monitor in this room, but it might seem kind of innocuous, but I went through and changed all the figures in my slides to make the loads a little darker because it seemed like on this monitor they were kind of light. So hopefully, is this a little bit more legible than it has been? Okay, good. The only other thing I wanted to mention was Blackboard. Okay, so first off, I don't know if something happened over the weekend, but Blackboard looks a little different. Like, I don't know if the layout's a little different. That isn't really the point. The big point I wanted to mention is that if you open up lecture notes and supplements, you'll see a lot more slides. I went ahead and basically uploaded everything except for our very last topic because I'm going to do that very different given the fact that we have another week in the class. So you'll see now, like for example, if you go into this topic, you'll see all the slides. And into this topic, you'll see all the slides and handouts. The only thing worth mentioning is I've got 1 slide here in topic 6, or 1 presentation here that I'm still sort of tweaking a little bit. So that one's currently being edited. This topic here, this topic 7, structural analysis using MassTan2. This is a software package that we're going to use a little bit later in the semester. It is both PC and Mac friendly, and it's free. Okay, so there's actually 1 homework assignment later where I force you to download it and install it and upload proof that you've installed it so that when we start doing it in class, I know it works for everybody's computers. But if you want to go ahead and install it earlier, I'm not going to stop you. Okay, sound good? All right, any questions? And did everybody get the code? Everybody get the code? I'm seeing somebody reach for their phone because they didn't get the code. 2 people didn't get the code. 3 people didn't get the code. Somebody didn't get the code. Did you get the code?
Yes, sir.
You got the code. Okay. All right. Okay. All right, so I want to get into our lecture today, and I want to talk about solving joints using 2x2 systems of equations. Let me sort of explain what I mean by that. Let's go back to just making sure that we're good with our analyses. Let's make sure we're clear on the base assumptions. We're assuming all members are connected by frictionless joints. We're assuming that all the loads and reactions are applied directly at the joints. And at each joint, the centroidal axes of each member coincide. So that means that each member is only containing one force. And the question is it a tensile force, is it a compressive force, or is it a zero force? We have the method of joints and the method of sections, and today we're still talking about the method of joints. The big thing about the method of joints is that we are limited to members with at most two unknowns. Okay? But there's nothing that says that both of those unknowns couldn't be diagonals. Okay? Like, what if I'm solving a joint and they're both diagonal members? We're actually going to have a little bit of a problem with the way that we've been doing them up until now. So in order to solve those in a systematic fashion, we're going to have to break out a basic problem in mathematics, which is the solution of simultaneous equations. There's a whole class, there's a whole course in mathematics dealing with this called linear algebra. Anybody ever heard of linear algebra? This is what linear algebra is basically solving problems like this. And there's a lot of stuff that goes into it, but really the science of linear algebra started with these types of problems. Everybody in here has probably dealt with these types of problems at some point. Maybe you did it in high school, maybe you did it in Math 127 or Math 132, maybe in one of your calculus classes, but I guarantee you everybody has done a problem like this. So the idea is that, let's say you're given two equations, x plus 2y equals 3, and 2x plus 3y equals 4, and the idea is to find that magical pair of values, that value of x and that value of y, that satisfies both equations. See, you could rewrite these equations as an equation of a line, like solve for y, you get y equals mx plus b, y equals mx plus b. So you're trying to find that point where the two lines intersect in linear algebra. Now there's three practical approaches that you could apply. There's more than that, if you start getting into linear algebra land. But the most practical ones, or at least the two that you're probably most familiar with, are substitution and elimination. So let's just sort of review what that is. So substitution would be the following. So I've got these two equations here. I'd say, all right, let's take one of the equations and isolate one of the variables. So if I have x plus 2y equals 3, I can move everything all over on the other side of the equation and get x equals 3 minus 2y. And again, the method is substitution because I can take that term 3 minus 2y and replace that for x in the other equation. So the idea with substitution is use one equation to isolate a variable, then take that definition and substitute it into the other equation. Do a bunch of algebra, plug and chug and solve, and you get y equals 2. But then I can take that y equals 2 value, and it doesn't really matter which equation I plug it into. I can plug it into either one of them and get x equals minus 1. And there you go. There's the magical value of x and y that will satisfy both equations. I know it's been a while since you've done these types of problems, but I've got to believe everybody in here has done this type of problem before. Am I correct? It's been a while, right? Okay. This is the first method. Okay. The second method is elimination. Okay. Now elimination. This is. I'm going to bring up the Voldemort term here. I'm going to bring up MATLAB. Okay. Because I know MATLAB's like that which shall not be named, right? But this is kind of how software programs like MATLAB will solve simultaneous equations. What it will do is it will say, all right, let's take one of those equations and let's discover this magic number, and we'll call this magic number -2. Let's multiply the whole equation by -2. So instead of x plus 2y equals 3, I get -2x minus 4y equals -6. Okay, why did I pick -2? Because if I take the first equation and I take the second equation and I stack them on top of one another, I have a -2x here and a positive 2x here. So if I literally add up every term, so if this was all one big matrix, I would add up this row to this row. If I add up all the rows, then the x terms cancel, and all I'm left with is the y's, and then whatever's over here, then I get y equals 2. Take that y equals 2, sub it back in, and I get x equals -1. The same answer, right? Okay. I guarantee you've probably seen this. I know it's been a while, but you've seen it. Am I right? Okay. So this should not be that unfamiliar. Now, I want to be clear. I'm not going to make you do the problems this way. If you would like to solve the problems that we're about to do using one of these two methods, that's fine. Okay. What I'm going to do is utilize what it seems like everybody has in front of you, which is a calculator. Most scientific calculators will solve 2x2 or 3x3 systems of equations because they are so ubiquitous in scientific and engineering calculations. Now, the way that matrix algebra works is we say, okay, let's take this system of equations and let's write it in a tabular fashion. So what I'll do is I'll take this system and write it in this format. So this 3 and 4 just comes from this column of values over here on the right side of the equals mark. The x and y are my unknowns, and I just write them in order. So it's x and y, so it's x and y. And then this square block of coefficients comes from the equation. So I have 1, 2, 2, and 3 because the coefficients are 1, 2, 2, and 3. If there was a negative, I'd throw a negative in there, so on and so forth. Okay? The reason for writing it in this fashion is because the goal then is all I need to do is find the inverse of this matrix times that, and this is an operation that many calculators can do very easily. Okay. One of the things that you will see on Blackboard is if you open up the lecture notes section for trusses, I've included a playlist. Okay. Now my slides assume that you use this calculator right here, the Casio. Okay. And I do that because I believe that's what most of you used in Engineering 111. But if you have a calculator that's not the Casio, okay, I have a YouTube playlist that I've curated that has about 6 or 7 different calculators that walks through how to do a 2x2 system of equation solution. And if there's a calculator that's missing from that playlist, let me know and I'll see if I can find a video for it and I'll add it to the playlist. The way that you do that using a Casio is you hit the mode button. Now, whenever you're just standardly using the calculator, you're in mode 1. So once you're done with all this 2x2 stuff, if you hit the mode button and hit mode 1, you're going back to normal operation. That's computational mode. What we're going to do is we're going to go into mode 5. This is for 2x2 systems of equations, so 2 equations, 2 unknowns. This is for 3x3 systems. We're not going to really deal with many 3x3 systems in here, but we may, I don't know, near the end of the semester. But for right now, it's just going to be 2x2. And then what you would do is you'll get a little table that pops up on your screen, looks something about like this. And then what you'll do is you'll input, 1, 2, 2, 3 right here, and then 3 and 4 right there. And then let it solve, just press enter. X is minus 1, y equals 2. Now the calculator isn't going to know what x and y are, so what it's basically saying is that your first unknown variable is x and your second unknown variable is y. That's why it's saying x and y. So whenever you use this method, you just need to make sure you're writing your variables in order. And don't worry, that'll become clear as we do the problem we're about to do right now. Okay? Does anybody have any questions? Now, let's talk about why you would even need to do this method. Let's take a look at this truss here, this scissor truss. Okay, I have 4 joints, A, B, C, and D. I have all the loads applied, and I have the reactions shown. By the way, is this come through a little more clearly than it has been? Again, trying to make the colors pop a little bit more than they have been in the past. All right, can I solve joint B? Can I solve joint B right now? No. Why not? There's 3 unknowns, right? 3 members. What about joint C? Can't do that one either. Okay? So that leaves joint A and joint D. Okay? Let me show you what's going to happen when we solve joint A. Let's just do joint A, and you'll see what we're talking about. Let's see what happens. Okay. All right, so let's just do a little sketch here, just up here off to the side. So here's the joint, right? I have a load here, a load here. I have a member and a member. And then I'm going to get that, that, and that, right? I mean, that's what it's going to look like, right? So how many unknowns do I have in the vertical direction? How many unknowns do I have in the horizontal direction? Ooh, that's tricky, right? We haven't had that before, right? Usually we'll have like 2 unknowns in the horizontal and 1 in the vertical. And that says, okay, we'll do the vertical one first, use the slope ratio, and then do the horizontal, right? Or vice versa. But that's a problem here, right? We're not going to have that. That's going to be tricky, right? So instead, we're going to have to just solve both of them together. I mean, we could maybe use some trig and rotate some things, but that's really the crux of where we're at. So we're going to have to address this a little differently, okay? So let me show you what I'm going to do, okay? The first thing that I'm going to do is I'm going to make a little statement right here. Let's look at slope ratios. Okay, so let's just look at slope ratios. All right, I'm going to... All right, so let's just do this. Here, I'll do better. So I'm going to look at member AB over here and AC over here. Okay? And there's a reason I'm doing this. Okay? So let's look at member AB. Now member AB is this diagonal right here, and it's at a 1-to-1 slope ratio. Okay? 1-to-1 slope ratio. So if this is a 1-to-1, what is the length of the hypotenuse? Say it again. Oh. Pythagorean theorem. There we go, square root of 2. Everybody with me on that? So would you agree with the following statement? Would you agree that ABX is to 1 at, hold on, sorry, let me get that. There we go. As AB is to the square root of 2? Would you agree with that? So would you agree also that AB y is to 1 as AB is to the square root of 2? Does that make sense? So how about this? How about ABX is 1 over the square root of 2AB. And ABY is 1 over the square root of 2AB. Is that fair? Okay. The reason why I'm writing it this way is, yeah, ABX is an unknown and ABY is an unknown, but they are both dependent upon this. This is the real unknown, right? I mean, if you know AB, you can figure out that and you can figure out that. That is the actual unknown. So what I'm trying to do is write ABX and ABY in terms of the real unknown. And the real unknown is AB. Does that make sense? Okay. All right, so let's do the same thing with AC. So AC is going to look something about like this. And this is 1, 2. So if that's 1 and 2, what's the hypotenuse? Square root of 5. So would you agree that ACX over 2 is AC over the square root of 5? Like the horizontal component is to this as the hypotenuse is to that. And then the vertical component is to this as the hypotenuse is to that. Again, I'm trying to write the x and y terms as a function of that hypotenuse. Okay. Is that okay? Everybody okay with that? All right. So with that, now what I want to do is I want to do now my method of joints at A. Okay. Now, I'm going to throw something out there right off the bat before I write anything down. I am going to assume that both members are in tension. Okay? I'm going to assume both members are in tension. And there is a reason why. The reason why is that I'm ultimately going to use this equation solver here to do the problem. And so assuming that everything is in tension is going to make that part very easy. If I get a positive answer out of this little thing right here, it tells me the answer, the member is in tension. If I get a negative answer, it's in compression. So I'm just going to let the calculator do the hard work, but I am going to make sure that I'm using a consistent assumption. Okay? So let's see what we've got here. Now, again, going to do the problem the way that we've been doing it this whole time. So there's that. Here's my slope ratios, right? Okay. My loads on the joint. Right? 40 kips and 25 kips. And now what I'm going to do is I'm going to start listing my unknowns. Now notice I'm drawing everything in tension. Okay? Now watch what I'm going to do here. So here I'm going to say ABY, but I'm going to say 1 over the square root of 2AB. And here I'm going to say ABX, 1 over the square root of 2AB. And here I'm going to say ACY, 1 over the square root of 5. And I'm getting that. See what I'm doing? I'm trying to write everything in terms of my unknowns. And my two unknowns are AB and AC. So now let's do this. Let's be formal about it. Let's sum forces in the x direction. So what forces do I have going to the right? That and that, right? And then here, I've got that. Let's call that equation 1. Is that, am I going too fast? Is this good? Okay. So now what we'll do is we will sum forces in the y direction. Okay, how many forces do I have going up? 3. How many forces do I have going down? Nothing, right? So I've got nothing going down. And then going up, I have the 25 kips. I have ABY. And then ACY. So I get 25 kips plus 1 over the square root of 2AB plus 1 over the square root of 5AC is 0. And so what I'll do is I'll take the 25, move it over to the other side, and call that equation 2. That's going to be negative 25. Okay. Let me just take a second and let's make sure everybody's comfortable with what I've done so far. Now, here's the thing. Notice how I've been very cognizant in writing the equations sort of in alphabetical order. For example, the AB term, then the AC term. The AB term, then the AC term. The reason why that's important is because one question I'll get is, well, how do I know which is X and which is Y? It's the order in which you wrote them, okay? So I wrote the AB term first, then the AC term. That's how I know, okay? So now what we're going to do is we're going to solve this system of equations. Okay, so let me write these out. So equation 1 and equation 2 and then the negative. Don't forget that. So if we write that in matrix form, bless you. Bless you. Okay, and if we want to use the Casio to solve these, we take the mode button, then the 5 button, then the 1 button. And then the table that we're going to enter is so again, yeah, the calculator is going to say like A, B, and C, and then it's going to say 1 and 2, and that's what you're going to enter. And then when it's all said and done, the calculator is going to spit out the following. It's going to say X equals something and Y equals something. So I'm curious if somebody can tell me what the X is and what the Y is. Let's say in 2 decimal places.
Negative 127.28.
All right, so negative 127.28, and then what's y?
145.34.
Do I have a second?
Yeah.
So what that means is the following. That means that member AB is carrying 127.28 kips, and AC is carrying 145.34 kips. Now the question is, which is tension and which is compression? So member AB, is it experiencing tension or compression?
Compression.
Because it's negative, exactly right. And this one, tension. So to be clear, I'm showing you a way of doing this, in a calculator. I actually don't really care how you get from here to here. I'm actually going to leave that to you. If you want to do it by hand, use Excel. We are going to use Excel to do matrix math a little bit later. But again, you've got a number of different ways of going about it. Okay? All right, does anybody have any questions? This isn't too bad. Yes?
Yeah, it doesn't matter if we assume it's tension or compression as long as we notate well and keep track of it.
Yes, that's correct. Let me say this. It is advantageous, though, to get used to assuming tension because software packages assume tension. So when you run a truss analysis in a software program and it gives you a negative answer, more often than not it means compression. Now, let me qualify that. There are actually some programs that assume compression positive. It just depends on the program. So the one we're going to use assumes tension positive. So, all right. Sound good? Okay. I have something else I want to talk about today, and I want to talk about something that I mentioned last time, but I want to dig into a little bit this time. That's identifying zero force members. Do you all remember at the beginning of the example that I did on Friday when I said, I'm just going to look at the truss and say that number's zero? I didn't do any math, I just said, it's zero. No math at all. And I'm sure some of you were like, how did he do that? How did he just know? Well, there are ways to tell what members carry zero force without doing any analysis. So to sort of make the point, let me show you something. I have here, this is a truss from the textbook, and I can tell you that without doing any math, they're all zero force members. Every one of them. Okay, without doing any math. Now, we're going to get into identifying those here in a bit, but I'm sure some of you are sitting here going, hold on, wait a minute. Let's take a step back. Why would you even have a zero force member in a truss to begin with? Like, what is the point of putting a member in a structure that is not carrying any load? That doesn't seem to make any sense from an economic standpoint. Like, why would you waste money drilling holes in a steel member and making a gusset plate and erecting it and putting a member that isn't going to carry any load? Okay, there are two reasons, primarily, why zero force members exist. Now, the first, I'm going to go backwards, but the first is we have structures where loads move, okay? And we might have a situation, in fact, we are going to have situations throughout this class where, let's say we've got a big old truss and it's a zero force member when the loads are here. But once the loads move, now it starts to carry load, okay? There are plenty of situations in the land of bridge engineering where truss members sometimes carry load and sometimes don't, depending upon where the traffic is along the bridge, okay? So there are scenarios where zero force members are present. Another sort of, I don't know, it's going to sound like a cheap answer, but it's really not because we're going to be dealing with this next week, is whenever we do truss deflections, we have to do two truss analyses, and we call them a real analysis and a virtual analysis. And it's possible that during the real analysis it's carrying loads, but in the virtual analysis it's not. So there's that. But let's say, well, Dr. Mike, we still don't accept your cheap answers. We want to know, okay, is there another reason why a truss member might not carry load? That's because of what it's acting as. Truss members may serve as braces instead of meant to carry actual load. So as we know, truss members can carry either tension or compression. Now tension members will tend to just yield or fracture, but compression members carry a little bit of an instability problem. If you take a member and load it in compression, what does it have a tendency to want to do? Bend isn't the word I'm looking for.
Yeah.
I'm looking for it. That's an unstable problem. The word is buckle. Remember that from Engineering 216? That members in compression like to buckle, right? Braces can serve to increase a compression member's strength by so if here's the compression member and it wants to buckle, put a brace in the middle so that you reduce its buckling length and therefore up its capacity. That truss member may not be meant to carry load, it may be meant to brace the compression member, okay? So yes, zero force members are going to exist. And if you can identify them pretty quickly, you can make a truss analysis go really fast. And there are 3 pretty basic rules in order to do this. I would say that if we want to get down to brass tacks in theory, there's actually 2, but I sort of break it up into 3 because I think it's kind of easier to digest. So rule 1, no load applied at the joint, okay? So let's say I have a joint like this, okay? So it's joint out in space, and there's 2 members framing into that joint, and so I've got 2 unknowns, but there's no force applied to the joint. I propose that that is a zero force member, right off the bat. Now, that's not me, coming up with some magical rule. I mean, let's say I have a joint, I have a member here and a member here, so this has an unknown, this has a horizontal and a vertical unknown. So if I sum forces in the y direction, there's no vertical load, so that's 0. If that's 0, slope ratio tells me that's 0, and then if there's no horizontal forces, that's 0, right? So I'm not making stuff up, right? I'm just saying if I have a joint and there's no loads applied to that joint, those 2 members are zero force members, point blank. That rule also works if you had a joint like this. So let's say you had a joint that had like 4 members framing into it, but these 2 had already been determined to be zero force members, then these 2 are as well. Does that make sense? All right, any questions on that? All right, how about rule 2? Rule 2 is about when there's a load applied, but about the way in which the load is applied. Okay, so let's say that you have a scenario where you have a truss joint. There are 2 members framing into that joint, but there is a load on that joint. However, the load is parallel to one of the members, like this. I propose that's a zero force member. Now, how am I coming up with that? Again, same idea. Here's a truss joint, here's a member, here's a member, here's a force, right? Vertical, horizontal, horizontal. Sum of forces in the y direction tells me that's 0. Slope ratio tells me that's 0. I can't say this one's a zero force member because that one's got to carry that load. Okay? So there's a couple of other scenarios where this works. Here's a good one. This is a good place where this might work. What about a truss joint that looks something like this? I got a roller going like this. I got a force going in, no other loads. That's a zero force member. Okay? What about this? Same thing also works as if you had a situation where there's multiple members framing in, but they had already been determined to be zero force members. Same story. So far so good? That's rule 2. Rule 2 and rule 3 are kind of the same, but not really. I tend to split them up a little bit. So I say rule 3 is that if you had a joint that had 3 members framing in, and there's no loads applied, if 2 of the members are collinear, these carry the same force, and that's a zero force member. Okay? Same idea as before. Like if I put a vertical load, then this has got to carry it. But if there's no vertical load, then there's nothing that this is going to contribute. Does that idea kind of make sense? Everybody okay with that? Let's do it in practice. Let's look at this truss. Okay? This truss here is, now I put the answer in the slide, so I'm sure that it's possible to sort of cheat a little bit, but let's see if we can reason our way through this. I want to see if we can identify by observation the zero force members in this truss. And just to sort of like make the point, this is sort of a nasty looking truss. You know, there's members going all over the place. It doesn't make any sense. Now, granted, I do have that all of the members are at a 1-to-1 slope ratio. So this is at a 1-to-1, this is at a 1-to-1, 1-to-1, 1-to-1. That actually is relevant to the determinations that we're going to make. Okay? But let's see if we can identify some zero force members. And I will tell you that the easiest way to identify zero force members is to look at it on a joint by joint basis. Okay? So is there anybody here that can look at this truss from a joint by joint basis and tell me, is there a joint that pops out to you that say, hey, there's probably some zero force members going through that joint? Anybody find one?
H.
Okay, H. Okay, why are you, talk to me about joint H.
I don't know, it just looks like the other ones are 0.
You talking about this one?
Mm-hmm.
Let me ask you a question. Is she right? Yeah. Yes, you are right. There are no loads applied at joint H. These are parallel. If these are parallel and there's no load here, that's 0. That's right. How about another joint? D. Okay. What calls to you about joint D? Why are you looking at joint D?
There's no load applied to D, and there's the 2.
So there's 2 members going through D and there's no load applied. So that means that these 2 are zero force members. And is he right? Yes, he's right. Okay. Is there another joint that's sort of popping out? Say it again. A? F. Joint F. Tell me what's going on with F.
There's no load in the numbers.
There's no load, but there's a lot of members. We haven't yet figured out if these are zero force members. How about a joint closer to F? Not F, but another one close to it.
E.
What? All right, hold on. I got different answers. Okay, why are you saying E?
Well, the connection between F and E has to be 0.
This is a zero force member. So let's look. Okay, so let's look at joint E. There's a member, and a load. This we've already determined doesn't have any load in it, so we can sort of ignore it. So if you look at this joint and you have this member, and a load, what can you tell me about this joint?
EF is 0.
This is 0. Yes. So to go back to joint F, it is possible that there are some zero force members here, but it's also possible that this member, and this member carry load that just balances out. We have too many unknowns there to figure that out. But we're not done. Is there another joint that we can look at and say that there's unknowns? Let's before I answer that, or ask for an answer on that, let's look at something else. How many reactions does this truss have? 3. Joint A has that and that, right? Okay. What about joint G? 1. Which way? Horizontal? So I'll just draw it like that. The direction, whether it's left or right, doesn't really matter. So is there another joint that we should look at? G. Why G?
Because AG is going to be a 0 force member.
This is a zero force member. Why? Load, nothing vertical. You see what I mean? So these are all zero force members without having done any analysis. We took 5 members and said they carry no load. And we can get, so there's a couple other things that we can look at this truss and we can really start to do some analysis really fast. What is the load in member CE? 50 kips in what? What's up?
From point C.
So if you're analyzing joint E, you're saying this force is up. So is this tension or compression?
Tension.
Tension. There we go. There is no up. I get what you're saying, but that's ultimately what we're getting at. All right. How about this member? This member is going to carry whatever this reaction is, right? So without really doing any math, we've solved 7 members of the truss. Do you see what I mean? That's fast, right? Now some of you might be going, okay, yeah, Dr. Mike, but how many trusses are we going to have that contain this many zero force members? Just wait, because we're going to be doing real and virtual analyses, and the virtual analyses, very possible, okay? Very possible to contain a bunch of zero force members. That might not make a lot of sense right now, because you're like, what is a virtual analysis and what is a real analysis? Don't worry, that'll make sense later this week and early next week. But for now, how are we doing? Splendid?
Yeah.
So let me show you real quick what I have in store for your homework. So your homework,
I told her, I said, he's gonna make us analyze the entire
no, I'm not. Look at this. So problem 1 is only one problem, and I'm asking you to compute the forces on a single joint, and I'm giving you the reactions. See, I'm not
Do that
unreasonable.
Wednesday morning.
I'll do it Wednesday morning.
It's due Wednesday.
It is due Wednesday.
Is this one of those like Wednesday 9:30 things?
That's what she just said.
I know. I didn't put Roman numerals there.
I had to, dude, I got home last night from like Columbus,
I-
and I started on the homework. That's like due today, and I started on it because I got home from Columbus. And, I started on it. I had to finish it this morning, and I turned it in like right before it was due. I was like, I think it's. I took my time though. You know what I mean? That's just like, it was too late, and I was tired. I was like, I gotta go to bed. I was
If you
like,
met the deadline, you met the deadline.
Like, I woke up early, and I was like taking my time. Like,
Does everybody get the? Is there anybody, any other questions? I'm gonna stop the recording. So.